So as a very simple example, let's say A equals 20, B equals 30. We already found GCD and LCM, but just, investigating, the prime factorization, and just by investigating the common multiples and then choosing between the greatest one between the common multiples, and also looking at the least one between the common multiples, and also the common divisors, and the greatest one between the common divisors. But now let's find GCD and LCM using the prime factorization. So find GCD of A and B, LCM of A and B using prime factorization. So what was prime factorization of 20? 20 was 4 times 5, which means 2 to the power 2 times 5. And 30, the prime factorization is 2 times 3 times 5. Now, if I want to follow this recipe or this algorithm, look at the way we wrote A and B, the prime factorization of A and B. Here. The list of primes for A and B must be exactly the same. Both of them here are P1 to Pk. Now let's go to our example. So right now, the list of primes are not exactly the same. For the first one is 2 and 5. For the second one is 2, 3, and 5. So, but I can make them the same by including 0 powers if necessary. So for example, 3 is not appeared in the first list, but that's okay. I can just include 3 to the power 0, which is 1. I'm just doing this in order to make the list consistent. And so that we have the same list of prime numbers. Okay, now then, GCD of 20 and 30. Once you wrote it in the form that the same prime numbers are appeared in both, then we just need to simply choose the minimum power for each prime number. So the first prime number is 2. So power minimum number between 2 and 1. Then it's 3. So we have to choose minimum number between 0 and 1, right? Because the first for 20 power of 3 is 0. And then 5, minimum number between 1 and 1, right? Because both powers are 1 in the case of 5. So this is 2 to the power 1 times 3 to the power 0 times 5 to the power 1. And that's 10. Similarly, for LCM of 20 and 30, I have to choose, again, same recipe, but for each power, I need to choose the maximum power this time. So 2 to the power maximum 2 and 1, 3 to the power maximum 0 and 1, 5 to the power maximum 1 and 1. So this time this is 2 to the power 2 times 3 times 5, and the answer is 60. Okay, so also I want to give an example of the remarks that we said for the same example. We saw that the important remarks say that if you have a common divisor, always common divisor is a factor of GCD. And if you have a common multiple, always the least common multiple is a factor of the common multiple. So also note, if, for example, D2, if we set, let's say D2 equals 5, for example, a common multiple of A and B, then D2 equals 5 divides D, which is GCD, and how much was it? It was 10, right? 10 was GCD, and 5 divides 10. And if we set, let's say L equals 120, a common, oh sorry, this one was common divisor of A and B. And 120 is a common multiple of A and B. Then we can say that, as we call this one L2, then we can say L equals 60 divides L2 equals 120. So these are examples of remarks above. That GCD is not only bigger than equal to any common divisor, in fact, any common divisor is a factor of GCD. And similarly, LCM is not only less than equal to any common multiple, in fact, LCM is a factor of any common multiple. Okay, now another definition we need here is the definition of relatively prime integers. So given two integers, A and B, they are called relatively prime if GCD of A and B is equal to 1. So if the greatest common divisor between two numbers is 1, then those two numbers are called relatively prime. So let's say this is part A of the definition. Part B, given n integers A1 to AN, they are called a pairwise relatively prime relatively prime if a GCD of any two of them, any two distinct numbers, is 1 for I and J between 1 to N, and of course I not equal to J, right? So any two of them that you consider, any two distinct ones, their GCD has to be 1. In that case, we are going to call them pairwise relatively prime. So let's look at an example, and let's say a GCD of, for example, 10 and 39 is 1, right? Why? Because 10 is 2 times 5. 39 is 13 times 3. So if I make the list of primes the same, I can write this one as 2 times 5 times 13 to power 0 times 3 to power 0. And similarly, this one I can say 2 to power 0, 5 to power 0, 13 to power 0, 13 to power 1 times 3. And then that means GCD of 10 and 39, I have to choose the powers, the smallest ones. So 2 to power 0, times 5 to power 0 times 13 to power 0 times 3 to power 0, and that's 1. And if the GCD is 1, that means they are relatively, so 10 and 39 are relatively prime. If the GCD is 1, the numbers are called relatively prime. Okay. Now, another example. Let's say let A equals P be a prime number. Then P and B are relatively prime if P does not divide B. So if P is not a factor for B, then P and B are relatively prime. So if the number is not prime, that's not necessarily the case. For example, 10 and 25. So 10, if you think about it, 10 does not divide 25, right? But GCD of 10 and 25 is not 1. GCD of 10 and 25 is 5, basically, right? So if P is, so here 10 is not prime, so that's why although this A does not divide B, still GCD of A and B is not 1, and therefore A and B are not relatively prime. But if P is prime, once you know that P does not divide B, then you can be sure that P and B are relatively prime. So for example, 5 does not divide 7, and GCD of 5 and 7 is 1. So once you know that P does not divide B, you can say that you can conclude that P and B are relatively prime. Okay, so the proof for this is simple. So let me say then show that, because I wrote as an example. So solution. So P, and because P is already prime, so the prime factorization of P is just simply P to power 1. And prime factorization of B, let's say is, for example, P1 to power N1 times Pk to power Nk. And remember, if I want to find GCD, I need to make the lists the same prime factors appear in both. So then this one I can write it as P to power 1 times, let's say P1 to power 0 times Pk to power 0. And this one I can write it as P to power 0 times P1 to power N1, Pk to power Nk. And then for GCD, I need to list these prime numbers and then choose the smallest power for each. Choose the smallest power for each. So that means GCD of A and B is equal to P to power minimum of 0 and 1, P1 to power minimum of 0 and N1, Pk to power minimum of 0 and Nk. So this is P to power 0 times P1 to power 0, Pk to power 0, and the answer is 1. Okay, so in this case, A was P, that is a GCD of P and B. And then that means P and B are relatively prime. Okay, so then another feature, another specific exercise, it's also one of the book exercises for any two integers A and B, show that GCD of A and B times LCM of A and B is equal to A times B. So this is an interesting property that whenever you multiply GCD and LCM, you get product of A and B. So for example, if A is again equal to the example that we looked before, A was 20, B was 30. And we saw that GCD was 10, LCM was 60. So that means GCD of 20 and 30 times LCM of 20 and 30 is equal to 10 times 60, which is 600. And this is same as A times B. So this is an example of this. But of course, it's just an example, it's not proof. I signed the exam. Unfortunately, some students try to do the proofs with examples. So I always emphasize in all courses that I teach that whenever you want to prove a statement, providing examples is not a way to prove. So for example, triangle inequality, if you want to, some people wanted to show triangle inequality by providing examples that, for example, if x is equal to 5, y is equal to 10, then the inequality holds. Well, that's just an example of the case where triangle inequality holds, but it's not considered as a proof. So in the exam, if I ask you to show this, you cannot write this example. I see here I wrote example of this property is, for example, this one, A equals 20, B equals 30, then GCD LCM. It's not a proof. Proof has to be in general, not with examples, right? So how can you prove this? For example, you can work with an arbitrary A and B, write a prime factorization for A, prime factorization for B, right? So let me write hint for proof. Of example above. So we have A equals P1 to power N1. So use A equals P1 to power N1, P2 to power N2, Pk to power Nk, and then B, for B we had P1 to power M1, Pk to power Mk, and then GCD of A and B, P1 to power minimum, and 1 M1 to Pk to power minimum, and KMK, and LCM was P1 to power maximum, and 1 M1, Pk to power maximum, and KMK. So use this to show that GCD A and B times LCM A and B equals A times B. So just multiply the one in the third line and the one in the fourth line. So I almost told you the proof. Just multiply this guy with this guy and show that it's equal to this guy here in the first line times this guy here in the second line. Okay, now the next thing we want to look at is a Euclidean algorithm. Euclidean algorithm. This is an algorithm to find GCD of two numbers. So you may tell me that, we already have an algorithm to find GCD. What was the algorithm that we learned so far? That we need the prime factorization of A, prime factorization of B. Then we need to list the common prime factors, each one with the minimum power. We have to choose the minimum powers for each prime factor. Well, that's true, but that algorithm is time consuming. Sometimes in mathematics, if you have an algorithm, if it's time consuming, well, then we probably try to search for a faster algorithm, because efficiency is also very important, whether time consuming or not, whether even if you want to do it with a computer, still, even, we have, a powerful computer these days, but still we prefer to have a faster and time consuming algorithms that even computers can do it faster. So an algorithm to find GCD of A and B. So let me say faster than algorithm explained above. Okay, so this algorithm is based on one important property. So let me write it as a lemma. Let A equals BQ plus R, where A, B, Q, and R are integers. Then GCD of A and B is same as GCD of B and R. So let me prove this lemma first. Proof. So let D1 equals GCD of A and B. Let's say D2 equals GCD of B and R. We will show that D1 divides D2 and D2 divides D1. So this is a very useful trick that we use in number theory. So remember, let me compare this with the trick that we use in set theory. In set theory, if you want to show that two sets are equal, let's say you want to show set A equals set B. How would you do that? You would do that by showing that A is a subset of set B and B is a subset of set A, right? But in number theory, similar in number theory, if you want to show that two numbers are equal, one way to do that, if both numbers are positive, by the way, one way to do that is to show that D1, the first number, divides the second number, and second number divides the first number. So if A divides B and B divides A, in general, if A divides B and B divides A, then A and B, A is equal to plus or minus B. Maybe I can write as a note here, note if A divides B and B divides A, then A is equal to plus minus B. So this one you can verify it. That's true for any two integers, any two non-zero integers. But so this property means that if both numbers are positive, then if one divides the second one and second divides the first one, then two numbers must be equal if both numbers are positive. So here GCD by definition is a positive number. So if I want to show that D1 equals D2, I can show instead that D1 divides D2 and D2 divides D1. Okay. So we'll show that D1 divides D2 and D2 divides D1. So let's say to show D1 divides D2. So what do I know about D1? We know D1 divides A and D1 divides B, right? D1 is GCD of A and B, so divides both of them. Now, if I can show that D1 divides B and D1 divides R, what can I conclude? So let me see. So it's D1 divides B, I already have it. Now, I want to show that D1 divides R. What was R? R is A minus BQ, right? So D1 divides A minus BQ. Why? Because if D1 divides A and D1 divides B, then, so this was a property we saw before, right? So we saw, right, we saw that if, let's say, C divides A and C divides B, then C divides MA plus NB. So D1 divides A minus BQ, and A minus BQ is R. D1 divides R. So here, so we showed D1 divides B and D1 divides R. What does this mean? If D1 divides two numbers, then D1 divides GCD of those two numbers. Remark star above says that D1 divides GCD of B and R, which I called it D2. See? Here. We call this one remark star. If you have a common divisor of two numbers, the common divisor always divides GCD, the greatest common divisor of those two numbers. Here, what do I have? Here I have a number D1, which is a common divisor for, originally it was the greatest common divisor of A and B. But that implied that D1 is a common divisor of B and R. Why? Because R was A minus BQ. And if D1 divides A and D1 divides B, then D1 divides A minus BQ as well, which means D1 divides R. So D1 is a common divisor of B and R. So if D1 is a common divisor of B and R, it must divide the greatest common divisor of B and R. In other words, D1 must be a factor of the greatest common divisor of B and R, which means D1 must divide D2. Okay, so this part is for D1 divides D2. Similarly, what do I know about D2? We know that D2 is GCD by my assumption. D2 is GCD of B and R. So D2 divides B and D2 divides R. So that means D2 divides A as well. What was A? A is BQ plus R. A is BQ plus R. So D2 divides BQ plus R, again by the property that we said here. If C divides A, C divides B, then C divides MA plus NB. So D2 divides B, D2 divides R, so D2 divides BQ plus R. That means D2 divides A. So D2 divides A and D2 divides B. That means D2 is a common divisor of A and B. So that means D2 divides the GCD of A and B, again by remark star, which means D2 divides D1. So we showed D1 divides D2 and D2 divides D1, and both of them are positive. So that means D1 must be equal to D2. Okay, now we can use this lemma to find a GCD of two given numbers, which, as I said, is called Euclidean algorithm. Euclidean algorithm. Let's see how we can do that. So for example, let's say find, again, let's work with the same example that we did several times, 30 and 20. So we said that, okay, first we will, in the lemma, we said that if we do the long division, A as dividend, B as divisor, then we get A equals BQ plus R. And we want to find GCD of A and B, but then GCD of A and B is same as GCD of B and R. So we can reduce the problem, reduce the numbers this way, and continue it until we find the GCD. So here my number A is 30, B is 20. So I can say 30 is 20 times 1 plus 10. So see, this is my Q, and this is my R. And the lemma above says that GCD of 30 and 20 is same as GCD of 20 and 10. And then, so instead of 30 and 20, GCD of 30 and 20, I can find GCD of 20 and 10 because these two are equal. And how can I find GCD of 20 and 10? 20 is equal to 10 times 2. So if 20 is a multiple of 10, that means the GCD is 10. If one number is a multiple of second, if first number is a multiple of second number, then the GCD is the second number, right? So that means GCD of 20 and 10 is equal to 10. So this is because if, let's say, check that if, let's say, B divides A, then GCD, and A and B are positive, of course. B divides A and B positive. Then GCD of A and B is B. If one number is factor of the other one, the GCD is the number B in this notation. Okay, so here is algorithm. So the general algorithm, so the GCD is 10, which means that the GCD of 20 and 30 is 10, which is the original GCD you wanted to find. So here is the algorithm to find GCD. So we start with A equals BQ1, let's say plus R1, right? Then we know that GCD of A and B is equal to GCD of B and R1. Now, in order to find GCD of B and R1, we can repeat this process. So this time we do B, divide B by R1. It's going to be R1 times Q2 plus R2. And then GCD of, again, B and R1 is equal to GCD of R1 and R2. And again, I can divide R1 by R2. So by saying that, let's say R1 equals R2 times Q3 plus R3. And then again, GCD of R1 and R2 is same as GCD of R2 and R3. And we continue this process until we get, let's say, RK equals RK plus 1 times Q, let's say K plus 2. If one becomes the multiple of the other one, so see, these are I's. We have B and R1, then R1 and R2, R2 and R3. At some point, one of them becomes the multiple of the other one, and the remainder becomes 0. In that case, we can say GCD of, RK and RK plus 1 is equal to RK plus 1. So this is the end of the algorithm. So the algorithm finishes or ends once we get a 0 remainder. Okay, so let's look at an example. So for example, let's say if you want to find GCD of 662 and 414. Find GCD of 662 and 414. So in this case, my A here is 662, my B is 414. So first I need to divide A by B. So 662 is equal to 414 times 1 plus 248. So this is like my A, this is my B, Q1, R1. And then I have to divide B by R1, right? See? First A by B, then B by R1, then R1 by R2, R2 by R3, and so on. So B by R1, so 414 divided by 248, again times 1 plus 166. Now this is my B, R1, and now this is R2. I have to now divide R1 by R2. 248 is equal to 166 times 1 plus 82. And then this is again R2, and this is R3. And then again R2 by R3. So 166 is 82 times 2 plus 2. So this is R3, this is R4. Now R3 by R4, 82 is 2 times 41 plus 0. Once the remainder becomes 0, then the algorithm finishes. So this is, so that means GCD of 82 and 2, right? So this was R3, this was R4. GCD of 82 and 2 is 2, which means that GCD of the original two numbers, 662 and 414, is also 2. Because GCD of 82 and 2 is 2 because one is multiple of the other one. And once I see that one number is multiple of the other one, then I can say that GCD is the smaller number. 82 is multiple of 2, so GCD right now is 2. But GCD of 82 and 2 was same as 166 and 82. And that was, which was the previous step. And one step before that, 166 and 82 was same as 248 and 166. 101 step before that, GCD of 246 and 166 was same as 414 and 248. And one step before that, GCD of 662 and 414 is same as 414 and 248. So the idea here is to make the numbers smaller and smaller in each step until one number is a multiple of the other one. I have two numbers, 662 and 414. They were big numbers. But once I do a long division, I reduce the original GCD to 414 and 248. Then I divide 414 and 2 by 248. I do the long division, reduce the numbers. Which numbers? 248 and 166. Then again, do long division, 166 and 82. Again, long division, 82 and 2. But once I get 82 and 2, one number, which is 82, is multiple of the other one. So GCD is the smaller number, which is 2. And that means the original GCD that I was looking for must be also 2. Okay, so Euclidean algorithm is called Euclidean algorithm, which we can use to find GCD without doing prime factorization. Of course, doing prime factorization is also one alternative, but it's more time consuming, as we said. This one is faster. Okay, so another thing we want to look at is GCD as linear combination. Which is a theorem basically called Bezot's theorem. It's the name of mathematician Bezot's. Bezot's theorem says if A and B are positive integers, if A and B are positive integers, then there exists integers S and R such that a GCD of A and B is equal to SA plus RB. So SA plus RB, so this is called a linear combination. Called a linear combination of A and B. Linear combination means linear combination, for example, two numbers means the first number times a constant plus the second number times another constant. Similar linear combination of three numbers means first number times a constant, second number times a constant, third number times a constant, and then you add them all together. Okay, so numbers, the definition, numbers S and R in theorem above are called Bezot's coefficients. Bezot's coefficients of A and B. Okay, so again, let's look at the simple example that we had before. A equals, what was it, 20, B equals 30. And then we saw that GCD was 10. Now the question is, can I write this GCD as a linear combination of A and B, meaning that the A times a constant plus B times a constant, and I get GCD. So the Bezot's theorem says, yes, you can always write GCD as a linear combination of A and B. We didn't prove it, so we want to skip the proof, but just an example of this theorem. Just as an example, we will see an example and also some applications of the theorem. We'll prove the applications, but not the theorem itself. So in this case, if A is 20, B is 30, GCD is 10, how can I write 10 as, let's say, 20 times the number plus 30 times the number? Well, 10, we can write it as 20 times minus 1. Remember, the numbers are allowed to be negative as well. And B are positive integers. Then there exists S and R. S and R, we didn't say S and R must be positive. We're assuming A and B are positive. But S and R, we didn't say must be positive. They're just integers. In this case, 20 times minus 1 plus 30 times 1, and the answer is 10. So these are called Bezot, so minus 1 and 1 in this case are called Bezot's coefficients of A equals 20 and B equals 30. Okay, so now let's look at an application of this Bezot's theorem. Application of Bezot's theorem. So this is what your book calls it, lemma. So if A, B, and C are positive integers, and GCD of A and B is 1, and A divides BC, then A divides C. So let's look at an example first and we'll prove the lemma. So of course, you know that examples and proofs are not the same. Example is just an example. It could be helpful to give you some idea or to understand the lemma or theorem better, but proof is a separate thing. Proof is an argument that must be valid in general, not just for examples. So for example, let's say A equals 10, B equals 39, and 10 divides, let's say 390. Now see, here 390 means 39 times 10. So this is my A, this is my B, my C is also 10. Now the lemma says if A and B are relatively prime, meaning that GCD of 10 and 39 is 1, which is the case in this example, then I can say that A divides C. So 10 divides 10, which is true. So if A divides B, C, and A and B are relatively prime, then A divides C. So now proof of lemma. So let's look at the assumption. One assumption is that GCD of A and B is 1. If GCD of A and B is 1, the Bezos theorem says what? Says that some linear combination must be 1. So GCD of A and B is 1. That means MA, I'll call it S and R, I think. So let's say SA plus RB equals 1 for some integers S and R. Now I need BC to appear. So why don't I multiply both sides by C so that BC appears? So multiply with C. I get SAC plus RBC equals C. Right? Now A, what do I know about A? I'm assuming that A divides BC, right? So now A divides BC by assumption. A divides BC was my assumption. What else do I know? Also, A divides AC, because A is a factor for AC, right? So A divides AC. So now A divides BC, A also divides AC. So that means A divides SAC plus RBC. Again, because of the property that said if C divides A and C divides B, then C divides MA plus NB. A divides BC, A divides AC, so A divides any multiple of BC plus any multiple of AC. So A divides SAC plus RBC. And what is SAC plus RBC? According to this equation, is just C, which is what we needed. So with using Bezos' identity, you saw that the proof was simple. And now one exercise that you can check is that if P is prime and P divides AB, then P divides A or P divides B. So if P divides AB, now look, let's compare it with this lemma. Instead of A divides BC, here we have P divides AB. Now, if P and A are relatively prime, then lemma says that P divides B. But are P and A relatively prime? That depends. we know that if P does not divide A, then they are relatively prime. We saw this property before. Right? And in that case, you can conclude P divides B. And if P divides A, well, then you get what you need. Because you want to show P divides A or P divides B. Maybe I can write the proof. So let me write this one as example instead of exercise. See? So I can consider two cases. Case one, if P divides A, then we are done. Because I want to show P divides A or P divides B. So if P divides A, well, I get what I need. Case two, if P does not divide A, then A and P are relatively prime. i.e. GCD of A and P is 1. Why is that? We saw this property before. Saw this property above. Okay, and P divides, so P and A are relatively prime and P divides AB. So that means P divides B by lemma above. Now P divides AB and GCD of A and P is 1. So lemma above says that P divides B, which is also what we needed. Okay. And one more example. Let M be a positive integer. And A, B, and C be integers. If AC congruent BC mod M and GCD of C and M is 1, then A congruent B mod M. In other words, cancellation can happen in congruences if GCD of C and M is 1. If the GCD of the number that you want to cancel and the module is 1, if module and the number you want to cancel are relatively prime, then you can do the cancellation. Otherwise, you're not allowed to do the cancellation. Because it's an important property, maybe I can call it a proposition. The propositions are important statements, but normally not as important as theorems, or the proofs are not as long as theorems. So that's why I can call it proposition. So the proof, before doing the proof, I can give you an example. Let's say, for example, 10 times 2, let's say mod 5, for example, is same as 5 times 2. right? Because 20 and 10 are congruent mod 5. Because 5 divides 20 minus 10. And here, this is my A, this is my B. And this is my C, and this is my M. Now C and M are relatively prime. So that means I can do the cancellation. And I can say 10 congruent 5 mod 5, which is true. So if the number you want to cancel is relatively prime with M, then you can do the cancellation. So proof of proposition. Okay, what is my assumption? My assumption is that AC is congruent BC mod M. So assumption says AC congruent BC mod M. What does that mean? That means M divides the difference. Right? Which means M divides C times A minus B. That's the meaning of congruent. If two numbers are congruent, mod M, that means M divides the difference. Now, M divides C times A minus B, and my assumption is that GCD of C and M is 1. So that means M divides A minus B, right? Remember the lemma. The lemma was saying if A divides B, C, and A and B are relatively prime, then A divides C. So here M divides C times A minus B, and M and C are relatively prime. So M divides A minus B by the lemma above. And M divides A minus B means what? Means A is congruent B mod M. M divides A minus B means A and B are congruent mod M. And that's what I needed to show, right? I wanted to show that A and B are congruent mod M. Okay, guys, so that's all about this section. And 4.3, I think, yeah. And that's also next time we'll start a new section. So see you on Thursday.